Welcome to the GINSA Jupyter Notebook walkthrough. I'm Eric with the Wakeman Biodiversity Research Team at Hokkaido University. Here, we are at the GINSA GitHub repository. At the top of the page, we have a list of project files. Let's click the file named runginsa.ipynb. You are greeted with a preview of the Jupyter Notebook. All of this computer code is the same as the repository file runginsa.py. Jupyter Notebooks are advantageous because they let you run a program on a browser. We will run this Jupyter Notebook using the Google Colab service. Click the link Open in Colab. Then you will be redirected to the Colab interface for this notebook. This is the Google Colab interface for the Run GINSA Jupyter Notebook. First, check the top right status indicator to make sure you are connected to a runtime. If not, just click Connect. We are already connected. You can see that this notebook is composed of cells. Some cells have text, while others have executable code written in Python. The code cells have these white circles with a black play arrow. These are run buttons, and clicking them will execute the code in the cell. The first cell we run will install some packages required for using GINSA. So go ahead and click Run anyway. Now, the required packages are installing. You can see this happen in real time below the cell being executed. You will see a circle move around the Execute button as the cell runs. Here we run the cell that imports, or loads in, a set of programming tools required to use GINSA. And then we run the cell that defines all the core functions for GINSA. Jupyter Notebooks are cool because they let you see exactly what is happening to your data in real time. Moreover, Python is a very approachable programming language. Here we define the main function. This is the master control function that will determine GINSA's workflow. And finally, we run the main function, thereby starting GINSA. Next, we need to enter the path to our project folder. That's easy. We simply go to the top left icon that looks like a folder. Then, with our cursor over this field, right-click and select New Folder. Let's name this project folder project_directory. Hit Enter to confirm. Now we need the path to that folder. Easy. We right-click the folder and choose Copy Path. Paste in the folder path. Ctrl V. Hit Enter to confirm. Now, GINSA is asking us what species we want to search. Let's use the example of Lecudina longizima, since there are currently only 26 occurrences for this taxon. GINSA allows you to search single-word taxa as well. Be sure to get the spelling right. There should be no more than one space in there. And now, GINSA does the rest. Genus, Lecudina. Species, longizima. The first thing GINSA does is make a spreadsheet of all occurrences for your search. Then it makes a subfolder in the main folder for each occurrence. GINSA also gathers metadata pertaining to location and stores that data alongside the occurrence ID in the occurrences.csv spreadsheet file. Now, GINSA is performing its main task, which is to search out raw FASTA files for each occurrence containing metagenomic SSU sequences. GINSA will go down the list of occurrences, find links to the FASTA files on EMBI, then download the compressed files in each occurrence subfolder. After gathering all the FASTA files, GINSA will repeat the process for associated mapseq files, which helps sift through the huge FASTA files quicker. Now, GINSA has reached its decompression and deletion step. The FASTA and mapseq files were compressed, so they need to be decompressed for analysis. Since we don't need both compressed and decompressed versions taking up space, the compressed files are deleted. One obstacle we encountered when testing GINSA was space management. Lecodina longizima is manageable, but others such as Symbiodinium fill up our 1 terabyte hard drive before it even finished. We have reached the matching stage. Here, GINSA does a text search for Lecodina longizima in the mapseq files, then matches corresponding sequence names to sequences in the huge FASTA files. You can open the occurrence subfolders mid-run and see that now there's a FASTA and mapseq file in there. Sometimes there are multiple FASTA files. Sometimes GINSA fails to find any linked files. This depends on what data is available. GINSA then combines all the SSU sequences into a single spreadsheet file for each occurrence, which is now visible. If we open the file, we can see our extracted sequences. The run has completed with no errors. Success! Process details are printed out in real time to trace back any potential issues. We see nucleotide frequencies printed out along with a series of graphs. The first graph shows how many occurrence subfolders actually contain a full set of data. In our example case, we got 100%. Good job. For larger data sets, there will be some gaps. The next graph breaks down extracted sequences by length. Occurrence sources are labeled on the x-axis. We see some sequences were short, at 100 base pairs. Some sequences were longer. Most were between 200 and 300 base pairs in length. The third graph shows nucleotide frequencies for the entire seqmaster.fasta file. This serves as a quality control check. Nothing weird here. Finally, we see 2 documents in our project directory, along with the graphs as PNG files. Occurrences.csv can be opened and examined in the Jupyter Notebook. We can see the associated biogeographic data for each occurrence. Some data is missing. Again, data collection is limited by what is available. The seqmaster.fasta file is a collection of all SSU sequences accumulated during the run. These sequences can be augmented with location data in the occurrences.csv spreadsheet, depending on your research goal. Finally, since we worked on Google Colab's computers and not our own, we need to download these files. Simply click each file and choose Download. The files should land in your download folder. This was a walkthrough of the Run GINSA Jupyter Notebook. Once again, I'm Eric with the Wakeman Biodiversity Research Team at Hokkaido University.